Here's a classic related rate problem. It's the sliding ladder problem. You've got a ladder leaning up against a wall here. So I'll assume the wall is vertical. It's leaning up against the wall. I'll tell you that the ladder is a 25-foot tall ladder. Okay. Now, unfortunately for anyone standing at the top of the ladder, the bottom of this ladder is going to start to slide away from the bottom, from the wall here. And as that slides away from the wall, the top of the ladder, of course, will have to slide down. We'll assume that the top of the ladder always rests against the building. So as this slides away, this top moves straight down. The question is, if the bottom of the ladder is moving at 2 feet per second, then how fast is the top of the ladder moving when the bottom of the ladder is 5 feet from the wall? Well, I've got a rate of change here, 2 feet per second. That's, well, I know it's a rate of change because it's a, it's a ratio feet per second. So there's some function measuring feet that is a function of time, where my independent variable here is measured in seconds. So the thing is, this is the speed of the bottom of the ladder. So what I need is the position of the bottom of the ladder. So let's call this length x. So the distance from here to there is that length x, right? And dx dt then is the speed at which this x is changing, right? So this is dx dt. The question is asking how fast is the top of the ladder moving? Well, the top of the ladder, we need a position function for it. So let's call, again, from here, from the origin, let's call that length y. So dy dt is what we're looking for. So dy dt equals question mark when, and they told me x is 10, right? When the bottom of the ladder is 10 feet from the wall. So they told me how fast the bottom of the ladder is moving. They asked me how fast the top of the ladder is moving. I have a variable that's representing the position of this point measured from some fixed spot here at the base of the wall. That x is telling us where the base of the ladder is. Y from the bottom up is telling us where the top of the ladder is. And I know how fast x is changing. I'm looking at how fast is y changing. So they tell me dx dt, I'm looking for dy dt. What I need is a relationship between x and y that's always true, no matter where you are in this process, whether the ladder is standing up really tall or whether the ladder is really almost all the way down to the ground. What is the relationship between x and y? Well, the wall is vertical. This is a right triangle. It's always the case that x squared plus y squared is equal to 25. Here is an equation that relates x and y. That's always true, no matter what the situation is. I mean, no matter what the time is, right? What I can do now is, because I'm thinking both of x and y as functions of time, right? As time changes, x changes and y changes. The 25 doesn't change, that stays constant. But x and y are definitely changing. And so I have this equation which I will implicitly differentiate with respect to t. Implicitly differentiating here with respect to t, the derivative of a sum is the sum of the derivatives. So the derivative of x squared is 2x. That would be the derivative with respect to x. I want it with respect to t, so there's a times dx dt. Let's see if I can actually write a dt here. And then the derivative of y squared is 2y times dy dt. And that should equal the derivative of 25, which is 0. So I started off with an equation relating x and y, implicitly differentiating with respect to t. I now have an equation that relates dx dt and dy dt. I need to plug in everything I know and solve for the one I don't. So let's see what we have here. I've got 2 times x, so x is going to be 10, times dx, that's given as 2, plus 2 times y. I don't know what y is. And I'm looking for dy dt, so I better be able to figure out what y is. And this is a situation that comes up once in a while, actually fairly often, that I know one of the variables at the start, or at the time I'm interested. Can I find the other one? Well, I do have this relationship here, in that I know that if x is 10, then I ought to be able to figure out what y is. So y squared equals 625, excuse me, minus 100. So y is the square root of 525 times dy dt equals 0. And now I can solve for dy dt. Get a relationship between x and y, implicitly differentiate with respect to t, plug in everything you know, and you should know everything except for one thing, and that's dy dt. Solve for dy dt. So dy dt equals, what's that, 40 divided by, negative 40 divided by 2 times the square root of 525, which probably simplifies some. This is 25 times 7, so no, it's 25 times 21. 25 times 21. So you end up with negative 40 on the top. That's a 40. And 2 times 5 times radical 21 on the bottom. The 2 times 5 is 10, which cancels the 40, so I'm just left with negative 4 over the square root of 21. Which is equal to negative 0.87287, whatever. This would be in feet per second. Right? Notice the negative here. Right? Notice the negative. What does the negative indicate? Well, this is telling you dy dt, the rate of change in y with respect to time. With this being negative, it means that y is becoming less, right? So we're moving at 0.87 feet per second, but we're going in a downward sense, that this length y is getting smaller. And so dy dt is negative. What did we do, right? Every related rate problem is very similar. They told us about one rate. They asked us about another. Drew a picture here where variables are the quantities that are changing. This length is changing, that length is changing. These are the speeds that I know and the one that I don't know. Find a relationship between the variables. That's always true no matter what time you're looking at it. And then you can implicitly differentiate with respect to t to find an equation that relates the rates. Plug in everything you know, solve for the one you don't, and you've got it. There you go, the sliding ladder problem.